pieces, so obviously that attempt was unsuccessful. More to follow. Watch out, Bruce. So is anyone here from the Mossad? Do I have to leave to catch the bullet? Sorry, Bruce. It's part of the service. So without any further ado, we have Bruce Deng and Peter Ferret in spirit, who will tell us about Microsoft's efforts at analyzing Stuxnet. Take it away, Bruce. Big hand, please.
Yeah, so before I start, I don't want to say anything about the Mossad. But yeah, we had the running joke. So a few days, I heard some Iranian scientist got killed in a drive-by. Peter was talking to me, and then he's like, "Oh man, I gotta go." Somebody said, "Oh, he got disconnected from the network." Then he disappeared for a week, and I didn't know what happened. And then he came back like, "Oh yeah, Bruce, I was walking on the sidewalk. I got hit by a car." Yeah, I mean, you can't make this stuff up. So, anyways, Peter, so a lot of this, all this stuff, all this content here, the mistakes are mine, not Peter's. So, if there's something wrong, blame me, not Peter. Anyways, I'll start. So, one of the reasons for this talk is we actually planned this talk. Planned with Felix a few months ago, and at the time there weren't that many publications about Stuxnet of all the different vulns and so on. Task scheduler didn't get fixed yet, so we were planning to this would be the first time where we talk about this. So this is the reason. And the other one is we actually our team analyzed this Stuxnet malware within the first few weeks when it came in, but we weren't allowed to talk about it for very obvious reasons until now. I think this is the first time where I'm allowed to talk about this kind of stuff. So, and the other reason why is I want to share, instead of sharing, all this SCADA, blah, 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 blah stuff, I'm going to talk about how we actually analyzed it, the process that we went through, how we identified the vulnerabilities, how they were fixed, and the different people involved, and so on. So it's actually pretty interesting. So anyways, with that, I'll continue on. So I'm going to talk about how we, so there are two important, you guys know what Stuxnet is, right? So I don't have to sit here and explain. So there are to me, there are two aspects of Stuxnet that were interesting. One was the fact that it used 4 zero-day vulnerabilities, and the second part was the SCADA component. I am not a SCADA expert. I actually don't know anything about SCADA, so I'm not going to talk about that here. Peter did some stuff on it, but he's not here. So, and then if we have some time at the end, I'm going to talk about how we decompiled some components of Stuxnet. Rolf Rolls and I actually decompiled 2 components back to compilable C code, and we're pretty confident it's nearly identical to the original source code, because when we compile it, the opcodes match up 80-something%. So, but that's only if we have enough time. And then at the end, I'll talk about the lessons learned, what went wrong and how I could have learned this, how I could have analyzed this faster. All right, so the prologue to set the background for this. I don't remember what day this was, but it's somewhere in July. This one day, this company, this is an called VirusBlock ADA. They're a small AV vendor in Belarus. I've actually never heard of them. They sent this. They found the malware and they sent us a PDF doing some initial triage. And the PDF talked about. They show a screenshot which was then had some redacted. There's a screenshot and there's black spots there. And they're talking about the potential Windows 0-day using LNK files. And then later, we didn't get the sample, and then some guy from the AV test company sent them to us. And then at the time, there were also discussions on various internal mailing lists. People talking, oh, is this some new Windows 0-day? People were not quite sure yet. So, and then after we got the sample, the case manager actually opened a case, and they came to our office and asked, hey, people are talking about this. It seems like it's a pretty big deal. Can you guys take a look at it? And at first, the way he described the vulnerability, it says, oh, auto run through link files, blah, 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 blah. So at the time we thought, okay, well, just another auto run vuln. Why do we need to take a look at this, right? But at the end, we said, okay, fine, we'll take a look at it. And it's a good thing that we did. So I'm going to talk about how, I'm going to go, so there are 4 vulns. I'm going to talk about how we find each one of them and the techniques we use to find them. Okay, so the first thing. some more background. So you got to remember that when this came in, there were a lot of press talks, I guess, about this. People, they didn't know that there were vulns in there, but there were like a lot of press attention. We knew that there were other companies looking at this. We knew Symantec, McAfee, and pretty much all the AV vendors, all the other security companies were looking at this. It was important for our team that we need to know all the different, let me take this back a bit further. At the time, we did not know that there were 4 vulns in there. We knew there was only one vuln, which is the LNK one. We didn't know there were 3 more. But we knew that other people were looking at it, and so it was important for us to know, the details of the vulns, if any, before the other companies. Knowing first is pretty important to us because then we can tell our customers about them. We don't get money by publishing our results, so unlike other companies. Yeah, and another thing you got to keep in mind is Stuxnet is about a meg of code, like in binary form. So that's actually, it's not, some people think, oh, a meg is nothing. Well, actually analyzing 1 meg of binary code is a bit, not knowing what you're looking for. So, and we had a very short amount of time to do this because people were always, management were always constantly coming by asking us, okay, are there updates to this? Because the press requests, blah, 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 blah. So, and another thing is, when we're investigating this, there were a lot of expertise required because these vulns happen in different components in shell and win3k.sys. And although we have really smart people on our team, no one knows everything. So we need help from other people. So it's like a team effort pretty much. These are the facts, you got to keep these facts in mind. Like timing is really, really important. And also, you don't know what you're looking for. I mean, it's like all black box, right? All right, so the trick that we came up with was we divided, when this miner came in, we divided the task into two people. One was Peter Ferry, and one was the other person's me. And the way we did it, we were assigned to, basically they told us, okay, stop working on whatever you're working on, like spend full time on this. And the objective was that not to understand everything from the beginning to the end, but basically to identify suspicious blocks of code that may be related to vulnerabilities, and then isolate them and like try to understand them as soon as possible, and then pass that knowledge to the developer so that like they can figure stuff out. And like understanding every minute details is not important to us because that's like almost like not a waste of time, but it wasn't important to our team at the time. And then the other thing is that, so the developers, most of them, they don't read assembly code every single day, right? But they do know how the components they do know how it works and so on. So we need to transfer our reverse engineering knowledge to them. They can use that to try to figure out what the vuln is and vice versa. So, all right. So bug number 1. This is what we got. This is actually an unredacted version. So this is the file that we got from the sample. This is a link file. If you notice, there's like a path. It's like a .tmp blah blah path. So the first thing we saw, we looked at this file. Was like, okay, well, the link file is a binary file format. This is like when you right click and create shortcut, you create a link file. So the first thing we did was we converted the link in order to figure out what the vuln is for this. We knew that the path somehow the path to the file is somehow not validated properly, but we didn't know where that was happening. So the first thing we did was we dumped the contents of the LNK file into human parsable form. So all the different fields and so on. And then so we dumped it, and then here at the end, the path name is the CP1 name. It's actually like a structure, a field inside a structure in the LNK file. So this is a path. Normally you would see C colon whack blah dot C colon whack Windows System32 blah. But here they use a different format. But this path is basically, you can use this path as well. This path is used for removable devices. This one is for specific to a Kingston USB device. So the original sample came from, I guess, a Kingston USB stick. So we knew from the behavior of from the description that people were describing, we knew that the DLL that specified, like this file here is a DLL. We knew that was somehow being loaded into the export.exe. But we didn't actually quite know all the details at that point. So what we did was we just tell the debugger, hey, notify me when this DLL is loaded, and then so then when the DLL is loaded, the debugger breaks in, and we got a stack trace. And then from the stack trace, we figured out, okay, well, blah, it's pretty simple. We know where the vuln is, and this took like 2 or 3 minutes. Remember, so when we opened this case, there were probably like 20, 30 people involved, and emails were being exchanged back and forth, literally like every 2 or 3 minutes probably. So the root cause is basically LNK files contain links to a target, right? Shell needs to know the icon to represent this shortcut. And control panel links, which is a special type of link file, has a property called dynamic icons. And in order for the shell to get the icons, what they do is they literally call load library on this. And when anybody who programs Windows, load library, when you pass it, it will execute DLL main automatically. So the end result is that you get code running like in the current user context, like automatically. So the code path, this is that's actually, so this is the top, this is actually a stack trace. The top function here is, that's actually where a call to load library, and the bottom is all the functions that led to it. And I'm not showing the source code. I'm actually not going to show any, I'm not going to show any source code for any of these vulns, because these vulns are so simple to understand that like having source code is just like, it doesn't even matter. So anyway, so literally here with this vuln, you get to load library any file you want, okay? Then the file can be located anywhere. The attack vectors, okay, so once we figure out the vuln, okay, well, looks like the shell doesn't validate where the DL is being loaded from to get the icons. So, okay, but that was like, the one we made a repro with C colon Windows, C colon temp blah.dll. But we were wondering, okay, well, usually WebDAV, what if you put it, the DLL on a UNC share on the internet or something like that? Would this work? And that was important to us because that basically means that you can exploit this. You can put your file on the internet and you can destroy the world. So it turns out that we were able to create a repro that uses WebDAV, where the DLL is not stored on the local drive. It's stored somewhere on the internet. And when we found this out, it's like, wow, dude, it's like really bad stuff. So yeah. So of course, at the time, once we figure out, okay, all the different attack vectors, we know, okay, this is really bad. We need to act very fast. And of course, at the same time, there are management asking, okay, what are we going to do? Blah 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 blah. Of course, once we figure out the root cause, like literally about a minute or two after that, the fix was somebody recommended a fix. So the initial proposal for the fix is, okay, well, force it so that the DLLs can only be loaded from C Windows System 32, which requires admin to write to it first, right? It seems kind of obvious. But then the shell developer said, no, that actually we shouldn't do that because that goes against our public guidance to people. We tell people, hey, don't put your control panel files in in the Windows System 32 directory. Put it somewhere else. So if we were to put it, we had the first fix, then that would break a lot of third-party developers stuff, and that's like bad news. And we don't want to do that. So the final fix is actually different. We make sure that the applet, the control panel applet, is registered before we load the dynamic icons. So so that's how we fix that one. And of course, again, this happens literally within minutes after we figure out the root cause. And I think the fix was implemented this one we went out of band. So they built the final binder pretty quickly. So from the attacker perspective, like what the hell is this used for? Because with this vuln, all you can do is you can only get code running, but code running only in the current user context. So you're not able to load a driver or anything else. So it seems kind of useless, but it's actually not true. Because what is this used for? This is used for to gain an initial, footstep on the computer that you need on the target computer. And again, one thing you gotta remember is this is 100% reliable. There's no quote unquote memory corruption here, so it will be successful 100% of the time. And anyways, so this vuln, after we released a fix and stuff like that, we did some further investigation. It turns out this vuln was known for several years by various people. But of course, nobody told me about that. Yeah. Okay, so this is the one that we actually went out of band. This is within 2 weeks, I think, went out of band. And the reason why we went out of band is because once our team figured out the implications of this bug and how horrible it is, it's like, holy crap, man, we need to go out immediately. But of course, out of band is very expensive, and you need to calculate. There are many factors that add in. It's extremely expensive. I don't know what the figure is, but it's way more than my salary. And so we have to think about it pretty carefully. And we also look at some telemetry data. How we had some signatures being deployed for this particular vulnerability. We found that there were a lot of people being affected by this. So at the end, we decided to go out of band. And of course, Metasploit had an exploit for this, so 7-year-olds can exploit people. So it's pretty simple. So it's bad news. So that's how we went. That's how we went out of band. The interesting fact is, for this one, there was no reverse engineering required, right? Because we just had the LNK file, and we knew what was going on. So there's everything I just explained to you here happened within about 1 hour after we released a sample, setting up emails and adding the right people and so on. All right, so the next thing was bug number 2. So once we found the LNK file, that was pretty easy. It didn't require that much brain power. So the next one was, of course, I didn't know that we fixed LNK. We looked at LNK, we knew it was a bug. We didn't know there were more. So how did we find about the second one? So what happened was I was doing some analysis on this bug. And I ran out, of course, like most normal people, I analyzed malware in Windows XP. And I noticed that on Windows XP, yeah, I'm being serious. Most malware analysts use Windows XP, right? Yes, exactly. Even the VMs that people emulate, it's all Windows XP. So anyways, so I noticed I ran as normal user, and I noticed, crap, dude, there are rootkits being deployed. It's like, what the hell is going on? And then I told another friend of mine who is he works in the Windows team, and he's a Windows developer, so he works on Windows 7. So he ran this on his computer, and he's like, holy crap, man, that happened to me too. What the fuck? So at this point, you gotta remember, this is in the afternoon, right? This is late in the afternoon. I'm trying 5, 6 p.m. or something like that. So I'm like, holy shit, man, this is not good. So yeah. But the thing is, we knew that the rootkits were being deployed, but we didn't know how the rootkits were dropped, right? Because you need to install the rootkit somehow. We didn't know how that was done. And I clearly remember, at the time, I was exchanging an email with a buddy of mine, Frank Baldwin. I don't know if he's here or not, but we were exchanging some emails about this, and I asked him, hey, dude, well, I'm looking at this crap, and do you know how the rootkits were deployed, right? And of course, he lives in Germany, and where I live in the U.S., so our time zone difference, is bad. So we didn't get a response. So the following day, of course, we investigated. So when we investigated, the way we did it was we divided the task. I did my own thing, and Arthur did his own thing. So what Arthur did was he debugged this live. He looked at a window bug to export.exe and start tracing it. But as you know, like I said, there's a meg of code. So unless you know what the hell you're doing, you don't waste a lot of time, right? So of course that's what Arthur did. He spent a lot of time looking at this assembly and he didn't find shit. So he didn't make much progress. So he was really stressed out about this. Because again, when we told management, hey dude, looks like we have escalation privilege on XP and Win 7. What the hell do we do? They of course are freaked out, right? So they want results fast. So Arthur, the following morning, what he did was he used a different approach. Instead of doing live dynamic analysis, he used a process monitor and he looked at event logs. Being myself, I said, oh man, this is a waste of your time. Fucking process monitor is not useful for this. Nobody uses this for reverse engineering. I was wrong. So he looked at the process monitor logs and he found two interesting facts. He found that there were scheduled tasks being added. And he also saw that there were files being written, there's an XML file being read from the disk and then rewritten back to the disk. And so he didn't know where, because process monitor only tells you what's happening. They don't tell you exactly where in the binary that happens. So basically what we did was we had an internal tool and we were able to figure out, okay, exactly, we set a breakpoint on create file and we knew exactly where in the binary that file was being created and so on. So once we suspected that this had something to do with scheduled tasks, we added the developers of the task scheduler to the list. And of course, these people are mad smart, right? After a few minutes, we told them, here are the behaviors that we're observing. We extract the file before, the XML file before and after, and we told them, here, this is what's going on. Here's what we're seeing. Of course, the developer immediately said, oh yeah, dude, this probably has to do something with our CRC checksums. And of course, at the time I'm reading this, I'm like, no, dude, this can't be. So it turns out that this is the case. So the way it works is, I'll explain next. But yeah, they use a hash algorithm, and the hash algorithm was CRC32. And then, of course, I didn't believe him and stuff. So I looked at the Stuxnet binary, and I was like, yep, you're right. So the way here's how it works. On Windows Vista and higher, when you create a scheduled task, it actually stores all the information about the task in an XML file. And the XML file contains like which user the task is supposed to be executed as. So usually it's by you, right? And the task scheduler will checksum this XML file, save the checksum in a registry somewhere, and then before it executes, it hashes the file again, it checks to see if that is the same or not. Because when you create a task, you actually have readable, it's actually readable and writable. So anyways, that's how they did it. If the checksums don't match, and obviously there's some corruption, so we don't execute. But if the same, execute. But of course here, CRC 32 collision is very easy. It takes like, like 5 seconds to generate one. And that's what the Stuxnet author did. So the attack, here's how it worked. They create a task, which basically run DLL, while that's how it loads the driver. And then it checksums the file just before the file gets closed, and it saves a hash. Then it opens up the file again, and it keeps on padding the file until this checksum is the same. And that's boom, that's it. And then they disable the task and run the task again to bypass the caching stuff. And that's pretty much it. And what they did was they changed the current user to local system. So local system is like the highest privilege you get, I guess. So they get code running as root. Easy, right? Yeah. Yeah. So yeah, this is the reason why, again, this one I didn't have to show you any source code because it'd be worthless, right? I just be like, get CRC checksum. I think that's all the function is called. So anyways, so once we found this out, they're like, okay, again, this is within minutes after we figured this out and confirmed it. Okay, some guy proposed to change. Like, what the fuck? What do we do? So we said, okay, well, let's change the naive. So let's change the checksum. It's like, okay, instead of using CRC, let's use a stronger hash algorithm. So and then the next option, which came from another person, he said, okay, well, how about we change the permission of the task file? Don't only allow read access after the fact. Don't allow write access. So that that means they can't modify the file. And then the third option was, okay, we'll store the task somewhere else. Don't put it in an XML file on disk. So we'll put it somewhere else. Only system can read it. And in the end, there are different advantages and disadvantages for each of these solutions. Like primarily, a lot of this are backwards app compat issues. And in the end, option won. And so we changed the hash algorithm to SHA-256. And this update was released, I guess, last week. So that's it. So if you diff the fix, you'll see these new calls to use this SHA-256. So from the attacker perspective, so what the hell is this used for? So the LNK was used to get an initial foothold on the station, and it checks to see what operating system you're running. And if you're running Windows Vista or higher, it will add a scheduled task to run load a file, will run a function inside DLL, and then it will drop a rootkit. And again, this is 100% reliable because there's no memory corruption. You can't fail, right? So yeah, and the interesting is this thing only works on Windows Vista and higher. And now you remember at this time, yeah, it works on Windows Vista and higher because on Windows XP and lower, the jobs scheduled tasks are not stored in XML; they're stored in a different format. So anyways, so that's that's the task scheduler vulnerability. The third one is keyboard layout. So this one is particularly interesting because this one, I worked on this one. So you gotta remember that Arthur and I were working on this concurrently. We were trying to figure out how the hell our drivers being installed. So I used a different approach just because of experience, and Arthur used a different. So Arthur used process monitor and a debugger. So what I did was I used Windows XP and IDA. Okay. And of course, we observed different behavior. And, he was telling me on his computer, he saw, oh, dude, I saw the task schedule DL being loaded. I was like, dude, no fucking way. I don't see that shit happening on mine. So I didn't believe him. But I'm running on Windows. Of course, you gotta remember at this point, I did not know that on Windows XP it triggers a different bug. So I didn't believe him. I told him, dude, you're full of shit. It's not working. So anyways, so what was my approach? Actually, Arthur is. Arthur's really smart. He knew that, he's not hallucinating, so he convinced me. He showed me the logs, and it's like, all right, dude, I believe you, but fuck, how come I don't see this shit on my computer? Of course, at the time, I didn't even think that he was using Windows 7, and I'm using Windows 6. I didn't think about that. Anyway, so what I did was, yeah, it's horrible. So what I did was I statically analyzed the binary, starting from main, and I traced there from there on. And then after a few hours, I figured that we extract, there's an unpacked binary and there is some encrypted files in the resource. I extract that and we start analyzing it statically. So I looked in this file, and this file, let's see. So when I analyze this, you gotta remember, this is a meg of code, and I don't I only have a few hours to look at this stuff. And in the beginning, what Stuxnet does, it loads up this DLL hooking so they can load DLL in memory rather than from disk. So it's like a lot of work. It's like, I don't know, it's probably like over 1,000 like lines of assembly to do this crap. And it's like really complicated, I guess. So I wasted mad time doing this. Of course, I didn't get anywhere, and I still couldn't figure out what the fuck, why is my Windows XP being owned? So I looked at one of all the binaries I extracted from the resource section, and one of them had had strings that had win3k.sys and so on. And I knew from the dead listing, I knew they were searching for something inside win3k.sys. But the question? Oh, okay, sorry.
Please save your questions till the end.
So yeah, so the logic for this is like kind of complicated. It's like fucking, you look at the control flow graph, it's like, I don't know, like probably hundreds of like basic blocks, and it's like crap. I manually went through it, and I knew it was searching for something, but the overall picture was not very clear to me. So at this point, this is suspicious to me. Again, things to remember at this point. Management needed actionable information, so they need to make decisions, what to do and so on. So they need like answers like very fast. I'm constantly reminded, other companies are working on this as well. I think Symantec even had a blog at this time talking about this stuff. Of course, they haven't found this yet. But another thing to remember is, in reality, binary analysis is not like Pokemon training, right? It's like fucking hard sometimes. You don't know what the hell you're looking at, right? It takes time and patience. And people are constantly asking you for answers and blah, 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 blah. You can't make up an answer and tell them, because that's like bad news. So it's like a lot of pressure. Thank God my management is like pretty smart. They know that this stuff takes time, but they still want results. So, yeah, I mean, no, I'm serious. Sometimes like some managers, they think, oh, if you know how to use IDA, then therefore you're a reverse engineer. It's like, dude, like it doesn't work that way. And you try to explain to them, they don't understand. But yeah, thank God, my managers are really smart. So, anyway, so at this point, I'm like hella stressed. So I took this home. And I realized that going through the code line by line would be very time consuming, and I wouldn't get the results in time, and somebody might beat me to it. So it's not like cut it. So what I did was, I used all the facts that I knew from this binary. One, I knew that there was code that was searching for something inside win3k.sys. I knew that there is code that allocates memory using anti-virtual allocate memory. And then there's code that loads keyboard layouts. I have no idea what the fuck keyboard layouts are, but I just saw code that was using it. And then IDA failed to disassemble some blob of code, some blob of bytes, I should say, right? And that was it. These are the only things I knew. And at this point, I had a hunch. I knew that I was getting really close, but I couldn't quite grasp what the hell was going on. At this point, I had a pretty high suspicion that the bug is in win3k.sys. But I didn't know where, because win3k is massive, right? It could be anywhere. So my suspicion is like, okay, it's in win3k.sys, that's all I have. So you gotta remember, it's like pretty late at night, probably around this time, actually. So, after like a lot of stack analysis, I got tired, and so I thought, okay, how the hell do I come up with the result so that the following morning I had something to tell the team? So I went through a few thought process. I thought, okay, well, the first thing that came to mind was, one, hook up a kernel debugger, and I tell the debugger to tell me, I tell the debugger, say, hey, dude, notify me when this driver is installed. And from there on, once the driver is installed, the kernel breaks in, and I look at all the stack traces to see if there's anything that's like, suspicious. But again, of course, that doesn't work. This won't work because in Windows, drivers are loaded by this system process context, and like you won't get much information out of that. So that won't. So this first this first thought failed. So next one I thought was, okay, well that didn't work. So let me use another technique. So I said, okay, this must be a kernel exploit. Therefore, and exploits tend to crash from time to time. So because rarely you get 100% reliability, right? So I said, okay, well, the exploit is going to crash one point or another, and if it crashes, I get a blue screen. I get a blue screen, I get a crash dump. From a crash dump, I can like figure out what's going on. So this is the process that's going in my head. This made perfect sense to me, but I ran the fucking exploit like 10 times, and it didn't crash at all, and I still get on every single time. It's like, what the fuck, dude? And I thought this was like another logic bug. It's like something I'm missing here, right? So it's like kind of like discouraging. So the next one I thought was, okay, well, kernel exploits usually put shellcode in userland memory and then try to execute it there. Why don't I ask the debugger, hey man, when the kernel tries to execute some code in user mode, can you like let me know? Of course, this is wishful thinking because we don't have this. This functionality does not exist. Anyway, so I got like really like depressed about this. It's like, holy shit, dude, I need to have something the following day, blah, 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 blah. So I got tired, I went and looked at some porn. And so anyways, I'm just kidding, no. So I thought, okay, like I'm like really tired by this point, right? I'm like, fuck, dude, like this is like stressful. And so, so obviously the previous experiments failed, so I was like, what the fuck, what am I missing here? I need to rethink this again. So, okay, so I thought, okay, I have many pieces of the puzzle, but I'm like, I need to figure out, like, am I missing any other, like, crucial pieces? And I thought, okay, well, the only other piece I don't understand is, like, these blob of bytes that has no references to it in IDA, and IDA can't fucking figure out what it is. And I looked at this and was like, okay, I need to look into this. So I decided to look at this blob of code. And I saw this. This is the blob of code. It's, like, repeated a whole bunch of times, right? So how many of you, like, this is, like, stand out to any of you guys? Yeah, so this is like, so I was like, oh man, this code looks very, very familiar. So you recognize the E8 followed by a whole bunch of zeros, and of course I recognize the C3. So I was like, okay, all right, well, thought process again. These bytes are stored, stood out to me because three reasons. One, IDA didn't properly analyze them. Two, they had no obvious cross-references to them. And three, they had reminded me of shellcode, right, just from the byte pattern. So I had another thought experiment. I said, okay, well, if these bytes are shellcode, then they have to be executed somehow at one point or another, right? And since they'll be executed, if I patch it with OXCC and I hook up a kernel debugger to it, and the exploit is successful, my kernel debugger should break in because CC is an int3, right? So this is how I went about it, and this is how I thought out this process. I didn't know it was going to work or not. So I went out and tried. It doesn't hurt, right? So this, the byte pattern I just showed you is that. Like, it's like push, call plus 5, pop. This is pretty standard shellcode, right? But at the end, you see like exchange, EX, and ESP, and a ret. It's kind of like ROP style, but I'm like, what the fuck, dude, ROP? And usually people don't use ROP stuff in kernel when they use like in user mode. This is kind of weird. But anyway, so remind me to talk about the shellcode later, because it's actually pretty interesting. Like, the attacker may generate this code using some type of code transformation tool. So remind me to talk about it later. But anyway, so when I did this, yep, it looks like real code to me. So I patched one of it to CC, and sure enough, it led me in the right direction. I patched a whole bunch of the bytes to CC, hooked up a kernel debugger, ran it, boom. The kernel debugger broke in, and I got a nice stack trace. And from there on, I literally sent the email when I got the stack trace. Holy crap, man, this is a breakthrough. I knew I was getting close. So I sent the stack trace to the team at like fucking like 1 a.m. and I went to sleep. Next morning, we came in, and with the stack trace, we were able to figure out what the bug was. So the bug is this. Windows allows users to load different keyboard layouts. Like, for example, if you're in China or whatever, in the US, the keyboard layouts are different. You can load them. Keyboard layouts are loaded, on Windows Vista and higher, keyboard layouts are loaded from the system directory only. So you can't, only admins can write there. But on Windows XP, it can be loaded from anywhere. That restriction is not there. So in kernel mode, what happens is like inside the function that loads a keyboard layout file, there's an integer that's read from the layout file. And this integer is used to index into an array of function pointers. And then the index is not properly validated, so basically the attacker can control this, they can basically get the kernel to call anywhere they want. Right? But what the fuck, you can control the call what you want, but you need to know, like, you need to have memory allocated at the destination that you're going to call at first, right? So what the attackers did was, it's actually really smart. So the ANL SVK proc, that's actually the array of function pointers, right? And you see there are 3 function pointers there, like the top 3. Win30UK, KBDNS, blah, blah, blah. But then you see immediately a few bytes after that, you see the 60, 63, 62, 61, and 006E. So in Windows, the OX7, FFFF, and below is from in user mode. Anything higher than that is kernel mode. So what the attackers did was they search for, once they find the base address of this function, the array of function pointers, they start scanning down from there and to figure out where the next D word that is within the user mode range. So they found like 60, 63, 60, 61. Then they allocate memory at that exact address, and then they put code there. And then they change index so that the index will be 0, 1, 2, 3, 4, 5. The index will be 5. The kernel will call that function directly. And that's it. Now, one thing is that at this point, I should have realized that since I've analyzed a whole bunch of these Win3k.sys exploits, and every single time people need to map the null page, so they use NT virtual allocate. I should have like spotted that immediately. I should have like set a breakpoint there and you see what's being written there. But at the time, I guess when you're like under a lot of stress, you don't think through all the different options right away. But thank God, like the previous OXCC trick works. So, but anyways, so that's how the exploit works. So the attack from the attacker's perspective is, the task scheduler is only used if you're on Vista and higher. This vuln is only used if you're on Windows XP or below. Okay, and the exploiting the keyboard layout issue is actually pretty easy, right? I mean, I told you once you know what the details of the vuln is. I mean, it's like little kids can do this. My mom can do this. It's actually very easy. And then another thing is the attackers, the people who wrote this, their target environment must be somewhat diverse. It must have like XP and Windows Vista and higher. So they probably want to target everybody. So anyway, that's what I got out of it. All right, so of course, once we figured that part, I was like, oh man, this is like great. I found this. So I felt pretty good. So we found 3 vulns so far. And like, crap, like how can there be more? The ironic thing is like the guy who sits across from me, he told me, oh man, Bruce, keep on looking. There could be more in there. I told him, oh dude, like quit joking around. Anyways, one day, Kaspersky sends us an email. It's like, hey dude, we saw some traffic. That's some weird like RPC traffic. Like, do you guys see this? Can you take a look into it? It's like, no, because I don't run malware on the network and stuff. Because I run a VM, right, but I don't usually care about like network connectivity. I don't usually care about that stuff. And so I said, no, I don't know about this. So we said, okay, well, let me take a look at this. So what I did was, I just set up 2 VMs and then had them connect to each other, and I ran Stuxnet on one of them. And I went to lunch. And then I came back and I discovered, fuck, dude, the other machine got infected. It's like, what the fuck, how is it going? This is weird. Right? It's like one after another. Anyway, so this one is like, this one at least, there's no stack trace or whatever, but I have packet trace. So when the packet trace, I was able to figure out what was going on. I saw that it was enumerating printer shares, as connecting to the printer share using a guest account, and then it's sending like write data to file or some crap like that. And it sends like an exe over in a MOV file. So I looked at the RPC routines that was used, and I was like, yep, this is in the Spooler code, and the Spooler is creating a file. But this, knowing this doesn't actually help at all because this didn't make any fucking sense. Typically, the Spooler needs to impersonate the user who is connected to it before it performs an operation, right? Because it doesn't make sense for you to Spooler. Remember, Spooler runs as like system, so it's like highest privilege. So, and I was like, yeah, I've worked on Spooler case before, and like this logic does not make sense to me. How the hell is this happening? The file creation should have failed because guest accounts don't have privilege to create files in System32. So what we did with this, so we added the printer team. Once we found out this is related to printer, we added the printer team. We figured this out, and it turns out that there's 2 special cases. The 2 special cases. One is that if it's a guest account and you connect into the network printer, then the system will impersonate itself, which is like system, and it will do the stuff for you. Or if the shared printer is one of some list of like 15 printers or something like that. And I'm like, what the fuck? So there's this comment on top that says, oh yeah, we have to do this because on Windows XP, the guest account doesn't have privilege to do X, Y, Z, and therefore we have to use system to do it. So anyway, so we of course, once we figured this out, it took like 5 minutes. So the guy from the printer team, the guy literally had a fix within 5 minutes. Like, dude, Bruce, wait for I'm writing the fix right now, and I'm building the package. Like really fast. So anyways, but of course the fix was his initial fix only fixed one part. It wasn't a complete fix. Later on, we involved more people, and we found out that we had to fix other places. But yeah, so that's how we found the spool issue, thanks to Kaspersky. So the root cause is that, yeah, I just explained to you, Spooler basically you can share a printer if you allow a guest account. Guest accounts can connect to it, and then tell the spool, once it's connected, tell the spooler, hey, print this data to a file for me, and you specify the path, and then you send the file. And that's pretty much it. Now, but the cool thing is that this vuln only allows you to write a file anywhere you want. It doesn't allow you to execute the file. So that's where the MOV file comes in. This is like pretty creative because I didn't know about this. The MOV file is actually like kind of like compiled script almost. And they wrote the MOV file in system32/wbem/MOV. And I'm like, what the fuck is special about why this directory? It turns out Windows has a thread that continues watching this particular directory for new files being dropped in there. Once a new file is being dropped, it picks it up and it runs it. So yeah, yeah. Now you can remember, right? So people are thinking, okay, well, like, is that like a vuln? Like, no, it's not a vuln because like you need admin access to write files to this place anyways. And it's actually, it's not an exe that you run, it's like some compile stuff. But anyways, so what they did was they wrote a script that runs the exe file they just wrote, and that's it, yeah. Yeah, I'm not gonna talk about the details how we fix the print spooler because it's really complicated. But anyways, from the attacker perspective, so this vuln only exists if the printer server was allowing anonymous connections. So the target network that they were going after must have had servers with this configuration. That's why, I mean, otherwise there's no point, right? And this is the way Stuxnet spreads on a network. Once it's on the computer, it scans, enumerates all the shares around it, and then if it is connected, it uses exploit. So the attackers must have wanted like large-scale infections. I'm not sure why they want to do this, but that's what I think. That's at least my hypothesis of it. And the attack had good tricks too. For example, I didn't know about this moth trick, but they did. So the lessons I learned from this is doing like a thorough job is like really hard. It requires a lot of time, and in real life, when you're being asked questions like every few hours, it's pretty stressful, and like you don't have time to go line by line and explain it, right? Especially if it's black box and you don't know what you're gonna find, you don't know what you're looking at. So you gotta find a balance between there. And then so in my case, I learned the mistake from that was like I took the old school approach, which is literally starting from main and tracing down. That's like bad news. Don't do that. Only do that when you have time. But yeah. And the other one is like the ability to figure out important facts and then putting them together to see a bigger picture is really important. Like for example, in the WinThrough assist case, like I figured all this stuff out, but I couldn't quite figure out how they all fit together until like towards the end. So if you figure them out early, you can at least get some clues and it's easier for you to debug. And the other one is like work with other people. For example, Arthur, he doesn't like reverse engineer stuff, but he has good ideas, right? So I should have used, listened to him I should not have doubted him I should have told him that process monitor was useless for reverse engineering. So that was like bad of me. But anyways, yeah, work with other people, and also like one person, you're not gonna know everything. Like you don't know how Spooler works in and out. You have to talk to the guys who work on this every day, so they can explain stuff to you. Like you might be able to know one aspect of it, but there may be other aspects that you don't understand that may affect the end result. And the other one, okay, about the attackers. That's all the vulns. After that. I spent time decompiling the rootkit, and Rolf did the DL loading part. And like we spent a lot of time analyzing it. Since now we're pretty confident that we found all the vulns. I mean, literally, manager came in and asked me, Bruce, are you 100% sure that there's nothing else in here? And I said, yes, I am sure. And that was, thank God I was right. But anyways, yeah. So after that we had some free time, so I decided to take a look at this a little bit more. And based on like the way the code is written, I could tell that the malware components were written by different people. Like for example, the exploit were written by different people, and the rootkits were written by the rootkits. Basically, what it does, one is to hide files, the other one is to inject code into like userland. That's the SCADA infection stuff. So they were written by different people, and like the driver was built from probably like a removable media, because like when you create Windows drivers. And you build it with the Windows driver development kit, the build environment, it'll automatically embed the full path to your project in there. So I think the path they had was like B:\whack guava, something like that. So B drive is usually like removable, like probably like a floppy disk or something like that. I don't know. But anyways, the attackers were definitely aiming for 100% reliability and high impact. All the exploits I just explained to you like will run like 100% with 100% reliability. Like there's no crashing. So even the kernel exploits, right? So yeah, they really wanted reliability. Apparently, they didn't want the computers to crash, or they didn't want people to notice. Decompilation. I don't know if I have enough time to talk about this. I didn't prepare the slides because it's like really involved. There are different tricks when we. Okay. Wait, what does that mean? I have enough time? Not enough time? So, I I didn't put the details here because the topics was probably going to be like, once when I wrote the slides, I realized that the whole process of decompiling this back to C code will probably require another talk, so which will probably, Rolf and I will probably do at one point or another. So there are the different tricks when you decompile. So most of the time, like, you don't need to decompile stuff, right? You only need to do that if it's like, if you want to feel good or you want to test your skills. So before I've decompiled code before, but just like one function, like one or two functions at all. But I've never done like full program decompilation before. And this one seems like the target was good enough for me to decompile, so I went ahead and did it. And there's a Windows driver, and like the different tricks you have to use. Like for example, like there are a lot of compile optimization that you have to be aware of and figure out to go from the disassembly code back to the like the source code, blah blah blah. So maybe we'll talk about it another day. Yeah. Okay. Anyways, there are like a lot of people who worked on this, and they have to be thanked because it's like a lot of effort. Peter Ferry, who got who helped me reverse engineer a lot of this stuff, and he also found some of the SCADA stuff, but he's not here. Arthur, the guy who found the task scheduler. Mark Woe, who helped me work with the spool issue. Our engineering team, Ken Johnson, who was the one. So I was gone for a few days, so they assigned Ken Johnson to analyze the remaining binaries that we extracted, and he found the net API vulnerability. So there's actually 5 vulns. 4 of them are zero-day. The 5th one is this MSA 067. That one is also used to spread around the network. And then the Spooler team, Richard Van Eden, who worked on the task scheduler, and then Rolf Rolls, who he doesn't work for us, but we decompile stuff together for fun. And then the Kaspersky team in Moscow. Kaspersky is actually the only team, because they sent us the print spooler stuff, we actually share all the details with them, like all the vulns. We had a con call with them, and we shared pretty much everything we knew about the malware. And they did the same. And then we had an agreement that, yeah, we're not going to share this with other people. So they should be thanked for that. And like the guys in the Moscow office are really elite. So yeah. And then of course I want to thank the virus block AD in Belarus for sending us the PDF, and then the AV test guys for sending us the sample for analysis. And questions.
Questions. So if anyone.
Yeah.